I would like for you to take a second and graph this guy on your calculator. Getting rid of that table, go back, hit menu. Now you only have two options. And we want to remove the table, and then it goes away. Double click on the white space, scroll up, delete that guy. Parentheses for my numerator. Divide by parentheses my denominator. And I graph it. And it looks like a line, because it is, with one small situation. If we go back and do exactly what we did with our previous problem, menu, trace, graph trace, we press 3 because we're trying to figure out what happens as x approaches 3. And here it says, it's undefined. X equals 3 is undefined. Well, why is that? Take a look at what's going on in your numerator compared to your denominator. Let's talk about a couple things. First of all, this is a difference of two perfect squares, so you can factor it. If you remember, it's x plus 3 times x minus 3, the square root of the first guy, plus and then minus the square root of the last guy. Difference of two perfect squares, divided by x minus 3. So what happens is those guys end up canceling out, and this becomes x plus 3. So essentially, this equation behaves like a line because things simplify down and it ends up just looking like a line. The line x plus 3, y-intercept of 3, up 1 over 1, up 1 over 1. But there's one small change because we aren't talking about this line. If we wanted to talk about this line, we would write that. We're talking about this line. And this line has a denominator restriction for your domain. Remember that domain cannot equal 0. Your domain cannot equal 0. So if you had a 3 in there, a positive 3, your denominator would be, sorry, I'm getting a little confused. Denominator cannot equal 0. So your domain restriction says, hey, if x is equal to 3, then at 3 minus 3, hey, we would have a 0 in our denominator. No bueno. So all of that to say, that's why this looks like a line, and that's why it's undefined at 3. So when it's saying, hey, what's the limit of x squared minus 9 over x plus 3, or x minus 3 as x approaches 3? It doesn't actually matter what happens at 3. What only matters is what happens as you're approaching 3. So there is a numerical answer for this. The limit as x approaches 3 from the left-hand side, and then let's look at the limit as x approaches 3 from the right-hand side. I can trace, and notice that 2.7, I'm trying to figure out why that's not so visible. Everything else seems to be fairly. So as we're tracing through, we notice, okay, we're getting closer and closer, 5.7, maybe 5.8. Maybe if we zoomed in, menu, zoom in, we could try and zoom into that situation and then go back to graph trace. Nope, we can't really get in any closer, but we did notice that we're kind of on either side of 6. Again, we could get our table and take a look at it. Our split screen goes up by 1, but if we wanted to, we could change our table settings. So we start at 0. Table step means, do I want to go up by 1 every time? Maybe I want to go up by 0.1 every single time. So notice that your x values are now going up by 0.1. So if I quickly scroll down, all the way down to 3, we might get a better idea of what's going on. Whoop. Oh no. Hopefully you didn't just mess yours up, and I'll tell you what happened there is that here you had 5.9 and here you had 6.1. And so you'll notice that as you decrease those steps, if you wanted to go by 0.01, that you're getting closer and closer to 6 on the other side. So being able to look at a graph and being able to look at a table and say, okay, as we're approaching 3, both from the negative of 3 and from the positive of 3, what number are we approaching? And they both agreed on, hey, you're approaching 6. And since that behavior is the same, in other words, you don't have behaviors going somewhere else, you don't have a gap in your graph, then this is totally fine. So then the limit as x approaches 3 in general from x squared minus 9 over x plus 3 is 6. So this is just some notation, and the concept is pretty straightforward. What I want you to start to get used to is this notation. The limit as x approaches 1 from the left-hand side. The limit as x approaches 1. This idea of this being the actual equation or function, and you're talking about the behavior of that function, really the y behavior of that function as x approaches that thing. This is something that we've talked about a lot in class. We've just never really given it a name. And this is it. This is the first step when dealing with learning about calculus. I want to talk to you about one more thing, and then the next lesson that we have is going to bring it together and say this is why it's important. So limits are a thing that happen. We've kind of got an idea about it. And now the other thing I want to talk to you about is this idea of an instantaneous rate of change. I'm going to tell you slope of tangent line. And we're going to talk about what that means. What I want you to talk about first is this. The distance between Lusaka and Livingstone in Zambia is approximately 500 kilometers. On vacation, it took Filippo 5 hours to travel from Lusaka to Livingstone. What is Filippo's average rate of change? Rate of change is something that we've heard a lot. And if we can remember, rate of change is related to what other concept? Rate of change, hopefully you grabbed some clues from here. The rate of change is your slope. Your rate of change is your slope. So when I wanted to talk about this, we can think about this as a graph because I think slopes are much easier to think about when we're looking at it visually. Normally on graphs, our time, in other words, hours, are on our x-axis, and our distance, in this case, kilometers, are 500. And so there's this idea of at time 0, you've probably gone 0, right? And then it says, okay, well then 5 hours later, you've gone or Filippo has gone 500 kilometers. Now, if you had a constant rate of change, which is a line, right? A line has a constant rate of change. It would look something like this. But if you think about it, driving, you're probably not driving the same distance over time. You're probably not driving the same speed as you're going. And so what's going on here is that this could be your slope, but also it might not look like a line. It might look like this, right? Or maybe it looks like this. And so since we don't know what it looks like between those 2 points, we can just say, what's the average rate of change? So it's the average rate of change because it's not a line. We don't know that it's a line. And then rate of change is your slope. So we're going to treat it like a line in order to find the slope with acknowledging that it's average, that it's not necessarily this slope all the time. So finding it, it's your change in y, so 500, over your change in x, which is 5. And that's kilometers over hours. We could simplify it down to 100. And then these guys remain in fraction form, kilometers per hour. That is your average rate of change between the beginning and where he ended up. Your slope turns this idea of placement into speed, or as they like to call it in physics, velocity. So when you've been finding slopes in the past, hopefully you've made this connection, but if not, now's a good time, that when you're finding the slope, the relationship as y changes, how does x change? It often results in a speed of some kind, a relationship between those two variables. And having your placement, or like, I'm here at this time, 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 relating those together creates your speed at which you got there. So this is a concept that is actually super, super important. And it's really important when we start talking about derivatives, because I'll give you a hint, they're connected. So I just want you to keep that in mind, that your slope turns placement into velocity. All right, so let's look at this in a little bit more of a mathy way.